Hello, ladies and gentlemen. Daja Hao. So my name is Chris. Thank you for the kind introduction. Today I have the honor to be invited to give you a presentation comparing back-conduct technologies with other commercial technologies which are used in mainstream PV modules. So to give you an outline of my speech, first of all, I will go into compare basic concepts between different technologies, and then I will go and take a look at the performance evaluation of different technologies in terms of power output at STC and temperature coefficients. I will compare reliability aspects in terms of hotspot, thermal cycling, damp heat, PID, and UVID performance. And then I would also like to share some, I think in my opinion, very interesting test results. Standards which are beyond IC standards, which are more severe, and maybe they are more adequate to explore fine difference between different technologies. And I will conclude in the end. So let's start with the background. So over the past at least 25 years that I'm active in PV, I experienced a gradual transition from aluminum back surface field to TOPCon back conduct cells and heterojunction cells that we have these days. So there have been, all these years, there is a continuous effort into improving the passivation and light management, but also improving the efficiency of the cells. So we have seen, where is this? Maybe, yeah. So we started with PERC modules that we have like significant improvements in the passivation. Then we go into TOPCon, heterojunction, and back conduct. Actually, none of them is very new concepts for PV. What has been significant improvement is the cost reduction that these technologies have had. And now you see companies like ICO are producing back conduct modules, and they're cost effective. Right, so in the next generation, most likely we'll see a shift to back conduct cells, maybe tandem cells, because there are also new concepts come like perovskite cells that could potentially increase the yield in a tandem structure. This is a little bit if, because the stability of the technology is not yet proven. So in this speech, I will try to provide a data-driven approach and compare different performance aspects between different technologies. So let's start with characteristics of back conduct cells and modules. So the very first thing I want to say is that they are metastable. The metastability is caused due to different defects existing, let's say, the interfaces or passivation. And as a result, back conduct cells operate a different condition under light and a different condition under dark. This does not mean that the technology has a problem, but it's a, let's say, inherent characteristics of all. It's not necessarily for back conduct cells. Also TOPCon cells also exhibit some metastability, and heterojunction cells as well. Another important thing is that they have internal capacitance. So back conduct modules exhibit diffusion capacitance, which leads to high hysteresis effects. For example, I saw here that you have, like, depending on how long your sweep lasts during the IV scan, you can have, and also the direction forward, reverse, you can have very different performance IV curves. So typical pulse solar simulators struggle to accurately measure IV characteristics. At the same time, steady-state simulators are also prone to temperature effects. So in TÜV Rheinland, we have introduced a patented method that we call dynamic IV, which helps us achieve high measurement accuracy. Looking at the STC output of different technologies, it's no secret that back conduct modules have the highest efficiency. And the reason, there is a very obvious reason behind this. If you get rid of all the front metallization, you have no shading losses from the top conducts. So actually the cell receives higher effective irradiance. And you can see that also if you compare with top-con heterojunction and back conduct. So back conduct cells have the highest efficiency. Of course, there is also significant variation between top to bottom, different technologies, different manufacturers, but generally speaking, back conduct cells have the highest efficiency. So we also see modules now increasing the power output. Most PV modules in the market right now are in the range between 500 to 700 watts. And we see some modules exceeding 700 watts being introduced in the market, and probably they will grow a lot more in the years to come. Another very important aspect is temperature coefficient, and actually the most sensitive temperature coefficient to temperature is the temperature coefficient of Pmax or delta. So again, we compare not necessarily ICO modules with other manufacturers, but we compare many manufacturers here that produce back conduct modules, heterojunction, and top-con modules. The king of temperature coefficient is probably heterojunction modules. I have the lowest temperature coefficient from all technologies, but back conduct modules have also very low temperature coefficient. So they are not that far. Right, so heterojunction has the best temperature coefficient, and back conduct technology follows closely, outperforming TopCon, which is the one down here. And now we would like to go into reliability aspects. I would like to stop at hotspot test, where the test has been conducted according to 612.15-2. And here I would like to compare the maximum observed temperature that we have during hotspot test. Perhaps I don't need even to say that most of the PV modules that we examine in the lab these days pass. So I don't think it makes sense to see which modules, which technologies are capable of passing. All of them are able to pass. Therefore, I think it makes sense to compare the highest operating temperature, and we see that back conduct technologies operate at significantly lower operating temperature. And basically this is because, it has been already mentioned, back conduct technologies, essentially they have like a pseudo diode behind each cell, which allows the current to circumvent the normal current flow in the module and jump from one terminal to the other, like a pseudo tunneling effect, which basically then back conduct cells do not need to operate in deep reverse, and as a result, they operate at much lower temperatures. This is a significant benefit for the PV module reliability, and it will definitely enhance the long-term performance of the PV module and the energy yield. Looking at performance at thermal cycling, again, here the tests have been conducted according to 612.15-2. In this test, we vary the temperature between -40 to +85 degrees Celsius, and we repeat between these two for 200 circles, while we also hang a weight from the junction box, which is equal to about 5 Newton. So what I have seen that all technology groups, more or less, they showed similar performance. So thermal cycling, I don't think really depends on the cell technology. It probably reveals more information about the interconnection and soldering craftsmanship that the modules had. So I think it's also important to mention that if we go back 20 years and see the performance of all PV modules had at thermal cycling, the average degradation that we have was over 3%, over actually 3.5%. Therefore, all new PV modules behave significantly better comparing to, let's say 20 years ago. So this is very good news for the PV industry. And now we'd like to stop at dam heat. So again, the test is conducted according to 61215-2. We operate the test at 85 degrees Celsius, 85% relative humidity, and the test duration is 1,000 hours. Again, I do not see significant effect between different technologies. Probably depends more on the module structure, for example, encapsulant material and passivation layer. Most of these technologies employ POE, which is an effective barrier to moisture ingress. There is also a significant difference between top to bottom, as you can see on the top cell, very characteristically. Therefore, we should not take for granted that all technologies have excellent resistance to dam heat, to moisture ingress. Each technology should be treated separately. Yes, we can say generally we see very good results, but there are also outliers. Looking at PID, again, the test here conducted according to 61215-2. Here, we apply 85-85 conditions of the PV module and apply system voltage for 96 hours. We see that all technologies show similar PID resistance. Again, this test is more dependent on the module structure rather than the cell technology. Most manufacturers already mentioned they employ POE, which is also is basically forming a barrier which is resisting sodium ingress, which is causing corrosion and PID. We have also seen technologies which use now EPE, so basically it's a sandwich between EVA and POE, and some of them try to save cost and they have a very thin POE layer. And we have had also some failures testing these modules. But generally, most of the mainstream modules that we see here show excellent resistance to PID. Oops, sorry. Right, and the last thing which I would like to mention, is UVID. We basically have a standard. There is no IC standard available right now. There is a draft which is being circulated. And we also have a 2 PFGs, which is an internal standard from TÜV Rheinland. So basically what our 2 PFG says that you have to do 120 kilowatt hours per square meter exposure from the front and then turn it around and do another 60 kilowatt hours per square meter exposure. UV radiance from the back, and before you test the final performance and compare with the initial. So during also developing this standard, we also tested in different conditions. I have more data for TOPCon than I have for back conduct. Generally speaking, I think that most manufacturers have the effect under control. I don't see like very, very significant degradation either at TOPCon or back conduct, but I would also like to say that most of these results that I share here have been done with, for example, back conduct, the exposure doesn't go beyond 60. I firmly believe that we should test for longer exposure if we want to get meaningful results. So I don't think this will be like the full degradation that PV modules will experience if you do a longer exposure. But at the same time, it should be definitely around 50% of the total degradation that we experience. So I don't think that, like I mentioned before, I think most manufacturers have this under control. I would like now to move to the last part of my presentation, where we test performance of PV modules, not following IEC standards, but going beyond them. So we will explore the performance of PV modules under cyclic hotspot endurance test, which is something new. I will explain you later what it means. We will also perform an extended reverse current overload test, extended bypass diode thermal test, and also an outdoor shading test. Right, so without further ado, let's jump on the results. So cyclic hotspot endurance test. So when you conduct a hotspot test in IEC standards, you actually do one circle, one long exposure under shading conditions. And here we did something quite different. We did 30 circles, where also the standard duration was also extended. So this is far more severe. So what we have seen between two different modules, different technologies, one was TOPCon, the other was back conduct. We've seen that the most important takeaway from this is that back conduct cells, indeed, they operate at significantly lower temperature. That is very important for the long-term reliability. We also seen that one of these modules, after doing this cyclic exposure, deteriorated. So here it looks like we have some passivation issues. But looking at the total power loss, it was not so significant. I would also like to say that I take distances from this here that you see. Because imagine that you have a power plant and you have a shading object which shades the PV module every day. It's not going to be affected for 30 days only, right? This will happen thousands of times. So I think these power loss here that you have will develop into something more significant in the field. So takeaway, back conduct modules, yes, they have very good resistance to hotspot. Going to the next slide, we also did an extended reverse current overload test. So basically we short the bypass diode and we drive current through the modules, not through the bypass diodes. The difference is if we conduct the test according to 670-30, you do a 2 hours exposure. Here we did 3 circles. So basically we did exposure, we let the module cool down, we did another exposure, another cool down, and another exposure in the end. We see again that the cells operate at cooler temperatures, around 15 degrees here. There was also some minimal power degradation differences, like 0.4% benefit between the back conduct technology to TOPCon. And the most important thing here is that they operate at cooler temperatures. So this also, as I mentioned, will have significant benefit in the long-term durability of the modules in the field. We also did an extended bypass diode thermal test. So here you short the diodes and you drive current through the diodes, not through the cells. So what I show here has nothing to do with the cell technology. So we performed the test at increased module temperature and increased current injection comparing to the standard conditions which are applied in 61215. We've seen that the back conduct module had a lower temperature, which was around, I say, more than 35 degrees differences between all diodes. So as I mentioned, this has nothing to do with the cell technology. It probably shows that the module used a better junction box, or junction box had better quality of soldering. The last thing is the outdoor shading test, where we exposed 3 modules. One was unshaded. The second module, we used a single spot shading. So if you see there is a small red paper here, which was something similar we did in the field. So basically, one of the cells was half shaded. And the third configuration, we did large area shading. So basically the shading obstacles affected both substrings, which are connected in parallel, and there is a diode over here. So basically both of the substrings were affected. We have seen, again, significant temperature differences. On the single spot shading conditions, the difference was about 60 degrees, and the large area shading, the difference was about 40 degrees between Module A and Module B. Module B was a back contact technology. And to conclude, so back contact modules have the highest efficiency in the market. They have improved temperature coefficients. They have demonstrated they have excellent hotspot resistance. Comparing to all other PV modules, they are by far the best. They have also robust reliability in terms of thermal cycling, damp heat, PID, and UVID. It's also comparable with especially when it goes, when it goes to all these tests, it's probably comparable with other technologies such as TOPCon and heterojunction that we have tested. But I already mentioned that this is a very good news for me because knowing PV modules 20 years ago, they didn't behave so well. And last but not least, back contact modules maintain higher power output and they enjoy lower operating temperatures under partial shading. So I think all these factors are very important and it's very encouraging use for back contact technologies. So with this, I would like to thank you very much for your attention.